Hello everyone, welcome back to the channel. Today we are going to explore the single phase full wave controlled rectifier using a Thyristor in a Simulink. This is one of the important circuit in power electronics, widely used in DC drive, battery chargers and many electrical appliances. So the challenge with the rectifier is that we often need control over the DC output voltage. A simple diode bridge rectifiers always produces the same average DC. But in the applications like a motor speed control or adjustable power supply, we need a way to regulate the output DC. So therefore, we need a thyristor, and by adjusting the firing angle, we can control how much of an AC waveform is converted into DC. Firstly, the circuit setup. In our model, we start with the single phase AC source of 315 volt peak amplitude, which is about 223 volt of phase voltage, and I'm using a 50 Hz frequency. Then we use a full bridge of 4 thyristors. Each has a resistance of on-state resistance of 0.001 ohm, forward voltage drop of 0.8 volt, a snubber resistance and snubber capacitance as shown here. Finally, the two thyristors are connected in series, and two pairs of thyristors are connected in parallel with the load. From the positive terminal of your AC source, it is connected to the midpoint of a two series thyristors, and from the negative terminal of your AC voltage source, it is connected to the second pair of thyristors. And I am using resistive load for now. I will change my load later into an inductive load and show you the difference that we get in our output. Next is the gate pulse control. To control these thyristors or SCRs, we need a 2-pulse generator. The first one has a phase delay of 0.005 seconds. That means it will trigger at the 90-degree firing angle, and its amplitude is 1, period is for 0.02 seconds, and pulse width of 5%. Then the second is shifted by a half cycle plus a cycle that of a same delay, so 0.015 seconds in total, and it will generate a pulse when we reach at 180 degree. So when the first positive pulse triggers its first pulse, it controls the thyristor and this thyristor and the thyristor number 3. It will switch on and off these two thyristors, and the negative pulse, negative half cycles of your AC voltage waveform, the negative pulse generates and it will trigger and it will control the thyristor 1 and thyristor 2. I have source voltage or voltage measurement block to measure the AC voltage. Similarly, I am using another DC voltage or voltage measurement block to measure the voltage across the load I have one current measurement block. From the DC voltage measurement block, it is given to the mean of frequency of 50 Hz, and I can get the output DC voltage. I'm using a mux, and all the signals are given to the scope. Okay. You can see that our peak voltage is around. However, the first panel is a voltage difference. We have a source voltage of yellow waveform and a blue of DC output voltage. Blue is a DC output voltage waveform. Then in the second panel we have positive pulse generator, a waveform that will show you how pulse generator triggers its waveform. And third waveform shows you a negative pulse generator, and finally a current measurement or current waveform in the final panel. Okay. Now you can see that if I start from here and trace the AC waveform, this is a first positive half cycle and then negative half cycles, and it completes its one cycle here. So when we complete the one cycle, it is 2 pi. So angle is 2 pi, right? And this one is pi, and this one is pi divided by 2. So pi divided by 2 is, if you convert into the degree, then it will be 90 degree, and this is 90 degree, and when I reach here at the negative half cycles, it will be 180 degree. So in the first positive half cycle, you have all the thyristors in reverse bias, and it's not conducting. So your voltage at the DC, your voltage at the load is 0, and when you reach at the 90 degree angle, your positive pulse generator will trigger the first signal, and it will turn on the pair of thyristor. It will turn on these two thyristors. These two thyristors will be forward biased. It will conduct the current through the load and return back from this thyristor and back to the source. Therefore, we have our DC voltage output, or we have a DC output voltage. And again, when we reach here, these two thyristor will be reverse biased, and it will not conduct. Until here, the second pulse generator will trigger, and it will again start conducting in a negative half cycle for and that's how it continues, or repeat the waveform continuously. If you look at the pulse generator waveform, the positive pulse generator fires at 5 milliseconds, right? In the first half cycle. Then the negative pulse generator fires at the 15 milliseconds. Together, this ensures an alternate conduction of SCRs diagonally. Now, at the bottom panel, we have a DC current waveform. Since from here to here, there is no conduction of current through the thyristor, and it is blocked. Therefore, there is no current passing through the load. Once the thyristor is turned on using the pulse generator, then it starts conducting, and that same waveform, we have a current of amplitude of 32 or something, and the load experiences a current. Similarly, reaches to the negative half cycle and it is reverse biased. Then when the negative pulse generator triggers, two another pairs of thyristors turns on, and it conducts in from here to here. Okay, then you can see that we have a DC average voltage of 98.68. Now let's quickly change our load to RL load with inductance of 10 to the power minus 3. Yeah, that should be fine, and let's keep a resistance of 1 ohm and run. Now you can see that okay, now you can see that from from here to here it is normal, but now since we have a, when you reach here, the thyristor is conducting, and the there is a around approximately from here to here, there is a current flowing through the circuit. Therefore, the thyristor cannot block the current, and it still conduct. Therefore, we experience a negative DC voltage, which is undesired. Therefore, we will use one freewheeling diode. And connect this freewheeling diode in parallel to the, that should be fine. And let's see changes. Okay, now the earlier we had the voltage across the negative half cycle, so that was shipped using a freewheeling diode. Why we have earlier we had the negative voltage over here? That's because of the inductive load, and that is undesirable. So we are using a freewheeling diode to clean up our waveform and make our DC output more clean and usable. That's how a controlled rectifier works. So you can now say that we have completed, we have a complete walkthrough of a single phase thyristor, from circuit design to firing controls to simulation results. If you found this breakdown useful, hit the like button, subscribe for more uh, similar tutorials, and drop your questions in the comment box. Thank you for watching. I will see you in the next one. Thank you.